बस। All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good to hear. All right, so today is an exciting day. I know that I said we'd do this last time, but we got too caught up in Linux to actually start this. But now that we have Linux all installed on our computers, we are now ready to actually run OpenFOAM. So today will be the first OpenFOAM activity. So you'll be running the kind of the first CFD simulation that kind of everyone kind of runs, which is called the lid-driven cavity flow. So the situation is kind of like this. So you have kind of a square box here, right? So the lateral sides and the bottom sides of the box are fixed. And so, you consider them to be basically no slip. But the thing that's driving our flow is actually the top part or the lid of the cavity. We're basically going to move it to the right with the constant velocity. So you can basically assume that we have basically a conveyor belt on top there. And that what that's going to do is that's going to drag fluid to go along with it. And then eventually you keep this up long enough, basically the flow is going to come around, it's going to hit the wall here, it's going to has nowhere to go, so it's going to go and cycle around the cavity, and you have this kind of vortex that kind of shows up in your cavity just like that. Okay. In terms of boundary conditions, in terms of geometry, it's about as simple as you can get for CFD. So this is kind of, for basically any CFD class, this is the first simulation that everyone runs. This is the first simulation I ran as well. So you guys will get to experience the same thing as well. All right, so that's the plan for today is just to kind of walk through this case. We're not actually going to be doing too much. You'll see that OpenFOAM actually has a bunch of examples and tutorial cases built into it. We're mostly just going to be observing and kind of seeing how things are set up. Because I think, if you're using OpenFOAM for the first time, it's really nothing like you've ever experienced in terms of engineering software. It's very different compared to like SolidWorks. It's very different compared to like ANSYS. And so you'll kind of see what I mean. So, a lot today will just kind of be me just talking and just kind of looking at the settings files, but I think it's an important day that we have to kind of get out of the way. Okay. All right. So one announcement I have to make before we begin. Some of you may have noticed right before the class started is that I did finish grading the midterms. So the average on the first midterm exam was about 37 and a half out of 50. So basically, right 75% right on the nose, and so that's you guys did well. So I have the exams here. So I think once usually I wait until the end of lecture, but I think just today because it's special, it's an activity. Once we have a good break, I'll say you guys can come up and pick it up. Remember, for this class we have kind of our dual midterms where one is weighted higher than the other. So if you didn't do as well this time, remember you can make it up on the next midterm exam. And as always, please pick up your exam. Please check it. If I made any mistake grading the exam, I added up the points incorrectly, or anything, please let me know as soon as possible, just so I can, go in and correct it. Okay. All right. So that's the plan for today. Any questions I can answer before we get started? Okay. All right. So let's go ahead and get started. Okay, so I'm going to go ahead and kind of do a dual screen here. So, because we're going to be working right alongside Linux here. Okay, actually, I will clear my screen. Oops, and just go to the beginning. Okay, all right. So if you guys are following along, and feel free, to kind of experience today however you want. And so, if you want to kind of follow along with what I'm doing, definitely feel free to have your laptop out. But if you just want to sit and watch and just kind of watch the recording later, that's fine as well. Okay. Okay. All right. So, so like I mentioned, the biggest difference between OpenFOAM and probably a lot of the other engineering softwares that you used before is that there's no graphical user interface, right? So I think when you think of engineering software, I think most people are accustomed to, you want to use SolidWorks, so you have to launch the SolidWorks program, and that opens up kind of a whole menu. So there's no such thing in OpenFOAM. So OpenFOAM, there's no front end GUI. And so the way you kind of set up a case in OpenFOAM is that you basically you're going to edit all these text files that kind of define the geometry, they define the boundary conditions, they define the mesh that you're going to use. And then you just call OpenFOAM when you're ready to run the case. OpenFOAM will run the simulation, and then it will show you the results using another program called Pair. Okay. So actually, we're gonna spend the majority of time here in our Linux terminal. and then kind of go from there. Okay. All right. So the first thing, yes, question. Yes, good idea. Linux kind of naturally has this kind of night, dark mode thing. Sorry, I always forget to dim the lights. Okay. All right. So the most important thing to kind of learn when you're using OpenFOAM and just when you're using Linux in general is just you have to be organized with your files. Okay. So I know, everyone, there's a saying that, you can kind of judge a person based on how they organize their desktop on their computer. So that kind of goes doubly true for Linux. I think it's just a little bit more difficult just because it's all based on text commands in the terminal. You don't have physical icons or physical files that you're kind of moving around with a mouse. Okay. Okay, so the first thing we'll do is, we'll kind of make sure that we are in our base folder. And so if you ever want to return to your home folder, a very easy way to do that is to run a blank CD command. So if you remember from last Wednesday, the CD command is used to change your location into a folder, right? So usually you type CD and then the name of the folder that you want to go into, or CD dot dot if you want to return. If you just run CD by itself, it just returns you to your starting position, which is called your home directory. Okay. So if you're ever lost or if you ever, want to just return, you can just type CD and then it will return you to your home directory. Okay. Okay, and we can hit LS, and so these are the folders that I have here. So there's a bunch of random folders here just because we made them in the tutorial last week. Okay. Okay, so what I recommend is to make a folder to host all your OpenFOAM cases. So, don't just put them into your home directory. So you can run an mkdir command to make a new folder here. So I already have one. So I have this folder called OpenFOAM cases, but if you don't have one, you can type mkdir. I call it OpenFOAM cases. Okay. And remember, with file names and folder names in Linux, you don't want to use spaces because spaces are used to denote kind of the differences between different files or differences between different commands. So if you want to have a space in your name, you have to use an underscore or you have to use a dash. Okay. Okay. So you type mkdir. Actually, just for the sake of today, I will make a folder with you guys. Okay. So I'm going to make this new folder called OpenFOAM cases. I have to use capitals just because I have a lowercase one already. Okay. So you can see that made a new OpenFOAM cases. So let's go ahead and go inside it. Okay. So I'm going to type CD OpenFOAM cases to go inside. Right. So now we're inside this new folder. There's nothing in here because it's a new folder. Okay. Okay, and so we're going to copy the tutorial from your OpenFOAM installation into this folder here. Okay. Now, OpenFOAM has a bunch of these tutorials. I'll go ahead and show you just really quickly. Okay. So we're going to use the CP command. So remember, CP is the Linux command for copy and paste. So we're going to do CP-R because we're going to copy an entire folder. Okay. And we're going to go to this kind of special location on your computer here. Okay. Now, what you'll see here is that this is kind of a special character here. So you'll see this occasionally in Linux, where you'll see that you'll have pads or you'll have things in your system that start with a dollar sign. So the dollar sign is a special character that's used to denote a special, basically what's called an environmental variable. So it's a variable that's visible everywhere within your system. Okay. When you install OpenFOAM, OpenFOAM also set a bunch of these what's called environmental variables that you can use to access specific folders and specific features within OpenFOAM. Okay, so one specific tutorial or one specific variable is this environmental variable called foam underscore tutorials, and the case is important here, so you have to use all caps here, right? Okay, so I'm going to add a slash here, okay, because this is a folder. This is actually a specific folder in your system. And I'm just going to mash tab for now, just so you can kind of see what's inside it. Okay. Okay. So remember, when you use the tab autocomplete, right? Autocomplete will complete the name based on what you have there. But right now, we're just kind of viewing the folder here, right? And so you can see here that OpenFOAM has all these different tutorials for you. So there's tutorials on compressible flow, there's tutorials on film flow, incompressible fluids, incompressible fluids with particles. moving meshes, multi-region. So there's a lot of tutorials within OpenFOAM that you can view. Just if you ever want to see how different cases run. Okay. But for us, we're actually gonna copy a very specific tutorial here called the cavity flow. Okay. So from this path, we're going to go into the folder incompressible fluid. So that's INCOMP, and I'm going to do a tab, and then I'm going to type fluid, and then tab again. Okay. So our command right now is cp-r foam underscore tutorials slash incompressible fluid slash. Okay. Right. So you can mash tab, and you can see what's inside here, and so you can see there's a lot of tutorials inside here. Okay. So we are going to copy the folder called cavity. Right? So I started typing cavity, and then I type tab to autocomplete, and then I want to copy that to our current location, which is the period. Okay. I'll do this again, just so you can see. But I'm gonna go ahead and hit enter. Okay. So that'll copy the cavity case file or case folder into our current directory, and we can hit ls here, and then this little thing is in the way. Okay. And so you can see here that after we copied that, and we now have this cavity there. Okay. So I'm going to do this again just so you can see. But if you've already copied the cavity folder, you don't have to do this. Okay. So I'm going to clear it. I'm just going to remove the cavity folder. Okay. So just again from the top, I'm going to do cp-r. That's going to tell Linux that we want to copy the entire folder. We're going to use our environmental variable foam or $foam underscore tutorials. Okay. And then we want the path to the tutorial. So this is foam underscore tutorials, incompressible fluid, okay, cavity, and then dot. Okay. Remember, make use of the autocomplete once you kind of start typing some folder name just to help your typing. Okay. Okay, and then you hit enter, and then you should have a cavity folder after you hit ls. Okay. All right, any questions on that? Everyone able to copy the cavity case file into their folder? No. Okay. Let me go around and kind of see. And by the way, so the PDF for the activity is online. And so I today I'm we're going to go a little bit slow. So if you want to kind of jump ahead, you can definitely download the PDF and then just kind of work on that. I try to kind of make this as detailed as I can. You can see it's a 20-page document. But I'm going to go around occasionally just to help kind of people get caught up. Okay. Okay.
You order them first, I'll let you.
Okay. Yeah.
Joe. First. This is photos. Pulp and photos syllabus. Yeah.
By the way,
Oh, I'll get to that when you're November.
Okay.
Oh, I got a bone to pick with Windows, dude.
Okay. But I mean, it's working now, so.
So-
That's good.
Yeah. So it was the. I think that's what it happened.
What happened? Well, it works now. I don't know what happened with that command, but for some reason it was thinking that the dash bar was not a valid flag.
With the dash.
Oh, so now do.
Yeah. I don't know. Well, it works. Sometimes minutes be like that. Right, what's up?
How should we go?
That's good. That's good.
So. $100 there.
Oh my gosh, I'm so sorry.
It's okay.
Okay,
It's fixed.
Okay. okay.
So, he's helping try to install, Linux, not Linux, Linux and, OpenFOAM.
Okay. Mhm.
He got stuck on the bash.
It was the very last part.
Okay.
Putting something this in the last line and keep doing it when it says that there's an error, it's like a extra character or something, notable line. You just hide
Looks like it's there. This is interesting. Look, I think the source it.
That's fine. You can also keep place. Yeah. Oh, here's the line, I guess.
Go for it. If you wanna. Go for it.
Oh, okay, we're missing. Okay, here we go.
Oh, that's it?
Yeah.
Holy crap.
There was just one line missing at the bottom. How are you guys doing?
We copied that.
So that's it?
What happened?
And then this stuff I can have you here.
So we are actually copying the whole cavity folder, right?
Put it right?
So yeah, cavity, good.
Gotcha. We have to try and actually figure this, right?
Yeah.
Okay. There's MK or yes, CRR.
Just type C. I can't say it with only being sure.
Oh my God. This right here.
Yeah.
You know,
Show me pseudo, but.
yeah, you have to. I'll have all of this. I just go to. Here's the same issue.
Okay.
Cavities? Yes.
Oh, so you have to put a period at the end because we're basically copying the folder here for everybody.
What?
So you need a CP. Actually, you need.
Is it?
I should have taught you guys this last meeting. But you want to put it up there.
What's that, let's do it again? Big flip.
There you go. And then. There you go.
say, we restrict.
Okay, you're good. You guys doing okay?
Yeah.
Good?
Yes, bro.
You guys happy?
So.
You guys happy?
I don't know, I look down. Dude, look.
Oh, what a area.
You're praying is more.
No, it's fine. There's a three going on.
I know, that's.
I'm not gonna do it down.
Why?
You're talking.
One thing I just caught.
some reason, I decided to go back to it. It was took away. What are we doing? This is the hope. Yeah, well, I think you like a break. That's weird. We're trying to. Gotta get the Giants had a touchdown. That's my feeling.
Yeah, good. So Kathy is an older actor.
I did not like
there. So you're good.
You're like that.
Okay.
It's like.
I don't even know. How this is.
I think I might have had the wrong password.
Oh, because it's.
Oh, yeah. But the short thing, what you can.
Oh,
The short thing, what you can.
Yeah.
Definitely remember the
But is it make a new folder? When it's over the file already.
Well, remember your password.
Is there any way I can?
No.
No.
I mean, there is, but it's very difficult. It's like a system level password. You can hit Control C to exit out of the, well, yeah. Try to.
You did this.
Okay. Oh, yeah, no.
This LS.
Good. Okay. All right. That was a little bit more complicated than I thought it was gonna be. Okay. All right. So I know more or less a lot of we have a critical mass of people that have successfully copied their cavity folder here. So let's move on. Okay. All right. So remember the way OpenFOAM works is that we're going to be basically working within this folder. So remember, we're not launching an OpenFOAM program. What we're instead doing is we're basically setting all of the settings first, and then just calling OpenFOAM when we're ready to run the program. Okay. Okay. So let's go ahead and cd into our cavity folder. So let's do cd cavity. Okay. And so now we're inside our cavity folder. And you can see there are 3 folders in here. So there is a folder called 0, there's a folder called constant, and there's a folder called system. Okay. So basically every OpenFOAM case is going to have this structure. So you're going to have these 3 folders here, right? And basically our objective now is we're going to go into each of these 3 folders. We're going to be modifying the different settings files and basically setting them so that we are ready to run our case. Okay. All right. So first thing, we're actually going to visit the folders going from right to left. So we're going to go to the systems folders first, and we're going to see what files are inside there. So let's go into systems. And by the way, if you ever get tired of the Linux term, remember you can always do explorer.exe dot. Remember that? Did I spell explorer wrong? Explorer.exe dot. Wow, everyone is Linux is not being kind today. Whatever, we'll do it without the Windows Explorer. Okay, so let's go inside the systems folder. So let's do cd systems. Okay, so we're now inside the system folder here. Okay, so if you hit an ls command from inside system, you'll see that there are 4 files in here. So one called block mesh dict, another called control dict, FV schemes, and FV solution. Okay, so the dict there stands for dictionary. And I know I'm speaking fast. It sounds weird, but it stands for dictionary. Okay. Okay, so we're gonna visit these files going from left to right. So remember, each of these are text files, right? So to open up a text file, you're gonna type vim, and then the name of the text file. So let's start with the block mesh dictionary file. Okay. Okay, and I'm gonna zoom out a little bit just to make it a little bit easier to kind of see everything. Okay. Okay. So there's a lot here, and we're going to go basically kind of line by line here to kind of show you what this is. Okay, so this is your very typical OpenFOAM type of settings file. Okay, and so to use OpenFOAM, you're basically going to be modifying these text files to fit your particular case. Okay. All right, so this is one that's going to be part of basically every OpenFOAM case, and so what this file is going to allow us to do. This allows us to define our geometry, and it's going to allow us to define our mesh, okay? Now, for this particular case, right, our geometry here is basically going to be a box, right? So that's where our flow is going to be. And in fact, I have a figure here that kind of shows you what our geometry actually looks like, okay? All right. So we need to basically define our box geometry like this, where we have each of these vertices. So we have vertice 0 that's going to start at the origin, and then we're going to find each of the other vertices here in order, okay? Okay, so we go inside this file here, and that's what we're going to be looking at. So the first section that we're going to be kind of highlighting here is this section called vertices, okay? Now, this section called vertices, you can see here we have a list of 8 different points where each of the points is defined by its x, y, and z coordinates, okay? Okay, right? And if you count them, there's 8 of them, right? And so this first one here is going to be point number 0. The second one is going to be point number 1, 2, 3, 4, 5, 6, 7. Okay. So we start with 0 because this is a real programming language here. So everything starts with 0. Okay. But there are 8 points. And so if you actually look at these points here, and you look at their coordinates, so you can see that point 0 is at the origin 0, comma 0, comma 0, right? So that matches up with our geometry here, right? Our point number 1 is going to be along the x-axis, so its location is 1, comma 0, comma 0. And so that's this location here, 1, comma 0, comma 0. Point number 2 is up here, right? So that location is 1, comma 1, comma 0. And then point number 3, we come back to the origin of the y-axis, so that's 0, comma 1, comma 0. Okay. And then the next 4 points are exactly the same as the previous one, but they're going to be offset by 0.1. Okay, so the z coordinate for all of these 4 points here is 0, comma 0, comma 0.1, 1, comma 0, comma 0.1, 1, comma 1, comma 0.1, 0, comma 1, comma 0. Okay. So we're not changing anything in this file. We're just looking at it. Okay. And so in fact, we're going to be doing that for all the files here. But the point of this is just to kind of look and see what the format's like and look and see what we have. Questions?
So the geometry is not really cube, right? It's thinner on one edge.
Exactly. Yes. Yeah, so that's a great point actually. So, this particular case here is actually interesting because it's kind of like it's like a 2D case. We're actually only doing flow in the x and y direction. But OpenFOAM is actually physically incapable of doing 2-dimensional flow. So you have to actually set up every flow as if it's 3 dimensions. And so to kind of emulate that, we're basically adding a 3rd dimension here, but we're making it extremely thin. So that thickness direction and z direction, we're only making it 0.1 meters thick. Okay. But we're gonna have a dimension of 1 in every other direction. Okay. Okay. Any questions on just the vertices of our box here? Okay. Okay. All right, so that's the vertices part here, okay? There's some other stuff at the beginning of the file here, so you can see that basically every OpenFOAM file has kind of a graphic up here. This graphic is actually optional, so you can see that if you're familiar with the way C++ does comments, right? You can see that this entire thing is just one big comment here, so it's all just it's all just a graphic. The first thing that actually comes up in a OpenFOAM settings file here is this kind of definition for what the file actually is, right? So for the most part, you're not really going to be changing these, and so not until we do kind of more advanced cases, but it's kind of good just to kind of see what this part is right here. So you can see that this part here, this foam file, basically defines this as a file that is compatible with OpenFOAM. Its format is called ASCII. So ASCII is the format in a computer which is basically human readable. The opposite of ASCII is binary. So binary is something that's only readable by a computer. Okay. The class of this file is dictionary. So that's what it's not dic just to be funny. It's dic short for dictionary. Okay. Location is in the systems folder, and then the name of the file is block mesh dict. Okay. All right. All right, so another line here that you may find curious is this conversion line here, okay? So every OpenFOAM file that involves some kind of physical measurements of length is going to have an option for you to apply a conversion factor. And so that's what this line here does, is so that applies a conversion factor of 0.1 to everything. Okay. But for the most part, that everything up here you can, mostly ignore. That's not usually what we're going to change. But the first part where you do have to kind of pay attention to is the vertices, which kind of defines our geometry. Okay. Okay. So for the first two OpenFOAM activities, we're going to be defining our geometry like this. We're doing very kind of blocky type geometries. In OpenFOAM activity 3, that's the first activity where we're actually going to be uploading or importing a CAD file that you may have created in another software. So for those of you that have used OpenFOAM before, probably, activity 3 is probably what you're more used to using. But for now, we're just going to be defining our geometry probably in the most simplest way, just defining first. Okay. Okay, any questions on this so far? Okay, good. All right, so first step, define your geometry according to the vertices. Okay. Okay, so the next part that we're going to look at here is the meshing part. Okay. So you can see that there's another section right here called blocks. Okay. So this section here is basically going to allow us to define our mesh. Okay. Okay. So in this one line right here, there's actually a lot of really interesting stuff. So let's kind of go through the line here. Okay. So for our particular case, we have a very simple geometry, which is just, a single block. By the way, I apologize switching between the PDF and the screen. I know it's kind of flashbanging you guys. So we basically just need to define our mesh on this simple block right here. Okay. So the way we do that is we basically say that in this block, we want to apply a hexahedral mesh. Okay. So a hex mesh is one where your elements look like blocks, right? And so your elements are going to look like basically little cubes here. Okay. So kind of the fancy name for a cube is a hexahedron. If you've never kind of heard that term before, hex stands for 6. So it's basically a polygon with six faces. Okay. The next thing we're going to define is all of the vertices, or all of the points that define this region. And so we only have one region. We just have one region that's defined by our blocks. And so we're just going to list out our 8 vertices here. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. So this right here is a list of vertices. Okay. All right. The next thing we're going to list here is the number of elements that we want in each direction. Okay. So this is telling us that we want 20 elements in the X direction, 20 elements in the Y direction, or 20 cells, excuse me, 20 cells in the X direction, 20 cells in the Y direction. And in the Z direction, in this particular case, since our Z direction is very thin, we only just want that, we only want that direction to be 1 cell thick. Okay. Okay. So what that's basically saying is that, let me go back to the geometry here. So flashbang warning. Okay. Okay, so what that's basically saying is that in this direction of the geometry, we want to set it so that we have 20 cells that go across here, okay? So this direction, we want 20 cells. Okay? And in the Y direction as well, we want to set it so that we have 20 cells here. Bless you. Okay. And so if you want to refine your mesh, if you want to add more cells to your mesh, you can do so here. So instead of 20, you can set maybe like 40 cells or 50 cells in each direction. Okay. But for this particular case, or for now, we're just going to keep it with the fairly coarse mesh of 2020. Questions?
All this finite volume that we're not doing a finite difference.
Yes. So all this is finite volume. Yeah. So you're not going to be doing any of the theory or implementing. OpenFOAM has done that for you, but you do need to understand fundamentals of this is how a mesh works, how the boundary conditions works. Like that. Okay. Okay, and then the last thing here that we are that you can set here is called the mesh grading, right? So we're not going to be doing too much with this, at least not for the first few activities. But if you wanted to, you can set it so that you have different basically mesh sizes in each direction. Okay, so right now, we're applying a uniform grading, so that means that you have your box here, right? We have basically the same mesh size or the same grid spacing in each direction. Okay. But for some reason, let's say that you wanted to apply a different mesh sizing in the Y direction, you can apply that here as well, right? So you can change this from a 1 to a 2, okay? So what that basically says is that for every one element that you have in the X direction, you're going to have two elements or two cells in the Y direction, okay? But for this activity, we don't need to do that. We're not worried about that. So we're just setting a simple grading of 1, 1, 1. So that basically sets the ratio for every one cell in the X direction, have one cell in the Y direction, so on and so forth. Okay. Okay, so this section right here basically is going to define your mesh. Okay, any questions on that? Okay, good. Okay, so the next parts here you're going to see actually looks fairly long. But this is where we're going to define the different surfaces where we're going to apply our boundary conditions. Okay. Okay. So this will probably be the biggest section that you have in the block mesh dictionary file called boundary. Okay. So the purpose of this section here is basically to define or basically to name all the different surfaces in our model. Okay. And the purpose of this is so that later on we can refer to these surfaces to apply boundary conditions. Okay. So basically, every surface that we have in our geometry, we have to define them here and give them a name because we can refer to them later. Okay. Okay. So if you look at our geometry here, we basically have a box which is very thin in the z direction. Okay. Okay. So if you look at this box here, we basically have 6 different surfaces, right? So we have the surface that's in front, we have the surface in the back, we have the top surface, we have the 2 side surfaces, and then we have the bottom surface, okay? Now we're going to define each of them, according to a different name, okay? And the way we basically define them out is using the vertices of the mesh of the geometry that we defined earlier, okay? Okay. All right, so first surface that we're going to define here is called the moving wall. Okay. And so that is the surface we're going to apply the boundary condition on. So that is this top surface right here. Okay. Okay. So you can see here we're giving this surface here a name. So this the name of this surface here is moving wall. All is one word. The type for this this type of surface is a wall type. So we're going to say type space wall. Okay. Next, we're going to define the surfaces that define this surface here. And so you can see here we have a list of vertices. So this is vertex 3, vertex 7, vertex 6, and vertex 2. Okay. Okay. So if you go back to our PDF here, right, right, you can see that those numbers here refer to the numbers of the vertices that we defined earlier, right? So if you follow out that list of vertices, and so actually let me kind of do this so we can see both at the same time, okay? So you can see that this surface here is defined by point number 3, point number 7, point number 6, and point number 2, okay? So if you trace that path around all those vertices, you can see it forms that top surface there, okay? So that's why we're defining this as moving wall, and that moving wall is defined by these vertices right here. Okay. Now you can take that same logic and then use that to define the other surfaces as well. Okay. So the next group of surfaces that we're going to define here are the fixed walls. Okay. Remember, there's only one wall here that's going to have any motion, which is the top one, but the 2 lateral surfaces and the bottom surface are not going to have any motion at all. Okay, so we're going to call those fixed walls, so they're not going to move. Okay. Okay, so you can see that the first surface that's defined here on fixed walls is given by 0, 4, 7, 3. Okay, so let's trace out that path. So that's 0, 4, 7, 3, and then back to 0. So you can see that this collection of vertices that defines the left face. Okay. Next one we have here is 2, 6, 5, and 1. So that's 2, 6, 5, 1, and then back up to 2. Okay. So this right here is the right face, or the right wall of the box. And the last one here is 1, 5, 4, 0. So that's 1, 5, 4, 0. Okay. So of course, this right here is the bottom one. Okay. Now, when you're defining surfaces like this, it doesn't matter which order that you put the vertices in, that the exact order is or which comes first or which comes last is not too important. But you want to make sure that it does form a closed surface, right? So if you're following the vertices around, right, the assumption is that when you list out the last vertex here, then you're going to draw a line to the first one, and that should make a closed surface. Okay. So it doesn't matter if you start with 4, if you start with 7, you start with 3, as long as it's in this order here and it kind of forms that closed surface, that's all that kind of really matters there. Okay. So since those 3 surfaces we're going to apply the same boundary condition, we kind of group them together and refer to them as one name, which is fixed walls. Okay. Okay. Any questions on this? Yes.
For that, moving wall, fixed wall, why would you put a fixed wall? The moving wall, is that implying that there's a velocity there, but why would the bottom portion?
Yeah. No, it's a good question. So remember the boundary conditions that we're applying, all have to do with whatever situation that we're trying to model. So for this particular case, we're trying to model this exact situation here, where only the top surface is moving. You can set it so that the bottom surface is moving as well. In fact, one of the things you're going to do at the end here is you're going to apply different boundary conditions. So you can see what happens, if you do apply a motion on the bottom wall. But for this particular case, we're only going to have just the top wall in motion, just because that's how we define the problem to be. Yeah. Mm-hmm. Yeah, the boundary conditions is something that you have freedom to kind of choose these situations. Okay, any questions? Any other questions on this? Okay. All right, so the last surface that we're going to define here is the front and back, right? So that's going to be the front surface here and the back one. So remember how I said that in OpenFOAM, it can't actually run a 2D simulation, but we can actually run kind of a pseudo 2D simulation. And there's a special boundary condition that we can actually apply there. So we're gonna make another named surface here called front and back, and we're going to define those 2 surfaces there. So first one is 0, 3, 2, 1. So that's 0, from 0 to 3 to 2 to 1, back to 0. So you can see that is the surface that's on the back of our box. And the other one is 4, 5, 6, 7. So that's 4 to 5 to 6 to 7, back to 4. So that is the front surface. Okay. And you can see that the type that we're applying here is a special type of boundary condition or a special type of surface called empty. Okay. And that's kind of a special keyword in OpenFOAM to say that, this third dimension or this third surface is not an actual, we're not actually simulating in that direction, but so we're going to assign it as empty. Okay. Okay, so that was a lot of talking and we didn't even change anything, but it's important to kind of understand what this file is, because this block mesh dictionary file is really important for our cases. Question, yes.
Does the order of the numbers matter? Sorry, so does it have to go 0, 4, 7, 3, or can it go 3, 0, 4, 7? Can it go like
So the order of these numbers, it doesn't matter which one goes first, but as long as they form a closed surface, then that's all that matters. And so you can start this one, you can do 3, 2, 1, 0 for this one instead of 0, 3, 2, 1, and that would be the same thing. Yeah. Mm-hmm. Any other questions on the block mesh dictionary file? Okay. Okay, so let's go ahead and exit out of this. And so remember, we are in Vim, so we're going to do :X just to exit out of there. Okay. Okay, so that was the biggest file. So that was the most that we had to talk about in that file. The rest of the files here are pretty short. Okay. Okay, so the next file that we're going to look at is called control dictionary. Okay, so we're going to do control vim control dict and hit enter. Okay. And once again, we're not going to change anything here. We're just going to look at, see what's up. Question, yes. Yes, and so remember, to exit out of Vim, you have to be in viewing mode. So remember, there's 2 modes in Vim. So you can either be in editing mode or viewing mode. And so if you're not sure, just hit escape, right? So escape will make sure that you're in viewing mode for the text file. And then you're going to type in : right? So actually, if you want to see my inputs, the inputs are going to be in the bottom left-hand side of the screen here. Okay. So we're going to hit colon, right? And then X. And so hit colon X, that tells Vim that we want to save and exit our file and return to the terminal.
Or control.
Yeah. Yeah, so we're looking at the control dict file. So we're going to vim control dict. Okay. And so in this file right here, we're going to set a lot of the parameters for the time stepping. Okay. And so we're not going to get to unsteady simulations until after spring break, right? And so we're not going to do too much here. But just think of this file, this control dictionary file, as a way to set, I call them kind of overall settings for the simulation. Okay, so settings that don't have to do with the geometry, but settings that have to do with, the time stepping, the time step size, how many time steps, how often to save, things like that. Okay. Okay. So this file is a little bit more straightforward because you can see it's just a collection of different settings, right? And so kind of the format here is that you have the name of the setting, and then you have the what you want to set for that setting right afterwards. Okay. So for instance, there is a setting called solver, right? So OpenFOAM has give you an option or ways to solve for different types of flow. Okay. So you can solve for compressible flow, you can solve for multi-phase flow, you can solve for incompressible fluids, supersonic, subsonic, all that good stuff. Okay. So for this particular simulation, we're just going to run an incompressible fluid solver. So this is kind of the simplest thing you can do with Navier-Stokes. And so we're going to set our solver to be incompressible fluid. Okay. Okay. And then everything else here, I think, will kind of make a bit more sense, I think, once we kind of get to time stepping. But, you can see here that, we're going to run our simulation basically for 10 seconds of simulation time. So we're going to have a start time of 0 and end time of 10. Okay, so we're going to start from that start time and at the end time. Okay. Our delta t, this is our time step size. And so this is how much time is going to exist between different time steps. Okay. So this is delta t. Again, we're not going to get to time stepping until after spring break, but that's one thing to see. Okay. Another thing to note here is we can tell OpenFOAM how often we want to save our results. Okay. So this is basically telling OpenFOAM that we want to save the results every 100 time step. Okay. So this right here is how often to save. Probably the only thing you're going to really modify here. Okay. So when you're running CFD simulations, you want to be careful about how often you save your results, because if you save too often, what tends to happen is that you just kind of get overwhelmed with the amount of results that you have. It's really not necessary to save every time step, even though I think for people just learning how to do CFD, that's generally the temptation is, I'm doing all this work, I want to see all the results. But it's kind of too much, and you kind of overwhelm your system, you overwhelm your computer from the memory and from from all the different files that gets created. So, you want to be a little bit conservative in terms of how often you save your results. But you don't want to wait too long to save your results. Otherwise, you're not going to have anything to really look at. Okay. So we'll talk more about this, after spring break once we get the time stepping. But, for now, if you want to edit it, then you can do that as well. Okay. Okay, and the rest of these settings here, we're not going to we're not going to change too much about it, but it just tells you how much precision that you want, the format of the files that you want, whether to compress the results, all that good stuff that, we're not going to do too much for. Okay. But, even when we do get to time stepping, the only settings we're really going to change is basically everything that's north of this line right here. Okay. So even though it looks like a lot of settings, for the most part, we're not going to change too much. Okay. And that's going to be a theme for a lot of our OpenFOAM is that, OpenFOAM kind of gives you the freedom to do so many different things. But, for most situations, you're not going to change too much. You're only just going to change what you need to, basically to get the geometry, set to what you want it to be and the boundary conditions to be what you want. Okay. All right. Any questions on the control dictionary file? Okay. Okay, so let's go ahead and exit out of this. So let's hit our control or colon X, excuse me, to exit out of this one. Okay, so the next two files, I don't even have a section for them here in the PDF here, just because they kind of refer to some pretty advanced OpenFOAM settings. Okay, so we can just actually take a look. So let's look at the FV schemes file first. Okay. So the FV schemes, this lets you kind of tweak kind of the settings for the finite volume discretization. So there's different schemes that you can set, mostly for the linear solver, mostly for the gradient scheme. Okay. So one small reference here is that you remember when we were kind of discretizing our gradient our diffusion term in the class, we used a linear profile. Okay, so that's that there. So if you want to use a different profile for the diffusion term, you can set that here, but linear works fine for our case. And you can set different settings for the divergence scheme, the Laplacian scheme. So, again, this file, we're not going to really change anything for it, but it's there if you ever want to look into kind of advanced finite volume theory. And then same thing for the other one as well. So we go Vim FV solution. Okay. So this is kind of more settings on the linear solver. So this is kind of more advanced kind of solver stuff. Okay. So if this were kind of a grad only course, or if this course had a sequel, these would be the kind of the things that we would talk about in that course. But for kind of an introductory course to CFD, we're just going to run with kind of the defaults here. Okay. By the way, kind of a funny thing, little spoilers, but there's a type of method that we use in CFD called the simple method, but OpenFOAM kind of has its own version called the pimple method. So kind of an unfortunate name. It's an acronym, obviously, and they're not referring to acne on their face, but kind of an unfortunate name for that. Right. All right, so in the systems folder, there's 4 files here, but really there's only 2 files that you're going to be modifying. And really it's only 1 file, which is the Bach mesh dictionary file. The other files, for the most part, we're not changing them too much. But it is kind of important to kind of know what they. Okay. Okay, any questions on this? Okay. All right, so we're done with the systems folder, so let's go ahead and exit out. Right, and so remember, to exit out of a folder, you're going to go cd ... and so that takes you up a level. Okay, so now we're back in the cavity folder. So now we're at this place where we can look at the zeros, the constant, and the system folder. Okay, so let me go and clear just so that it's a little bit easier to kind of see. Okay, so the next folder that we're going to go into is the constants folder. Okay. Okay, so let's do cd constant, and so that puts us inside the constant folder. Right? And you can see here that there are 2 files in this folder, one called momentum transport, another called physical properties. Okay, so just like we did in the systems folder, let's go ahead and view these because these are just simple text files. So let's do Vim momentum transport. Okay. Okay, so you can see this file is fairly short. There's not much going on here. So inside this file, the only really relevant setting is we can set the type of turbulence model that we can use. Okay, so you can see that for this particular simulation, we are running an RAS simulation, which stands for Reynolds averaged simulation. By the way, I apologize for the Discord sound. I think my wife is sending me pictures of my son right now. Okay. So we are accounting for turbulence in this simulation. That's kind of what RAS allows us to do. But if you want, you can also change this to a laminar simulation. Okay. But again, this is one thing that unless you have a good reason to change it, I would not change this too much. Okay. But just know that this type of default simulation does allow us to account for turbulence if we want. Okay. And then the settings for the RAS model are down here, right? So the type of turbulence that we have is K epsilon, which is a very basic, very commonly used turbulence model. And you can see that we are simulating turbulence. So turbulence is okay. So after you guys took the midterm last week, I kind of planned out the rest of the semester. I actually don't think we're going to have time to talk about turbulence modeling too much, just because I want to get 4 OpenFOAM activities in. And so, if we do have time at the end of class, I do want to talk about turbulence a little bit because that is a big part of CFD. But there's enough that we can talk about on the laminar side. So again, not much we're going to change here, but it is good to kind of see what this file is. Okay. Okay, so that's momentum transport. So the only thing relevant in momentum transport is that this sets the turbulence model. Any questions on this file here? Okay. Okay, so let's go ahead and exit out. So let's do our : X. Okay. Next, let's look at the file called physical properties. Okay, so I'm gonna do vim physical properties. Okay. This is also another extremely short file here. So this is where we can set the material properties or the physical properties of the fluid that we are simulating. Okay. Now for our case, since we have just a single fluid here, the only relevant property is actually just the viscosity, right? And so we're basically just setting our viscosity equal to 1 times 10 to the minus 5, which is about the viscosity, which is about the kinematic viscosity of. Okay. One thing you'll notice here is that we're not specifying a density, right? So typically, for fluids, the two main properties that we think about for fluids is a viscosity and density, right? Kind of just like we talked about at the very beginning of class. We don't use density here, and there's a very good reason for that, which is because OpenFOAM uses a kinematic version of Navier-Stokes, where we take density and we basically divide it by the entire equation. Okay. So density actually is not a variable, which is actually very interesting. It's kind of a unique thing to OpenFOAM. I would say most CFD solvers don't do that. They let you specify density. But because OpenFOAM uses that kind of special kinematic version of Navier-Stokes, the only property we need is the viscosity. Okay, and so this file here allows us to specify that viscosity. Okay. So if you're working with a different fluid, and let's say you're working with like air or you're simulating honey for whatever reason, you can change its viscosity here to suit your needs. Okay. Okay. Any questions on the physical properties file? Yes. Yes, you can. Yeah, so that would be a multi-phase flow. So multi-phase flow, you can simulate multiple fluids at the same time. So I'd say the most common case for that would be air and water. So if you are simulating, let's say like an ocean wave that's breaking on a coast, like you'd have one region that's air, another region that's water. So you can set the properties separately for this. Yeah. Mhm. There are tutorial cases for multi-phase flow. So if you actually want to run one on your computer, you can just copy the tutorial case into your. Those are pretty complicated though, so we're not going to do it in class. All right, any other questions on physical properties? Okay, okay, all right, so let's go ahead and exit out of here. Okay. So again, we're not changing anything. That's kind of the theme for today. I'm just going to be talking this whole time, but that's how you change the parts if you want to. Okay. Okay, so the last folder we're going to go into is the 0 folder, right? So it's kind of a strange folder name, but you'll see why it's named that in a second. So let's do CD0, okay? And if you hit LS, you can see that there are multiple files here, but we're only going to look at a couple of them, right? So we're only going to look at U, and we're only going to look at P, okay? So let's look at the U file first. Let's do vim U, where U here is capital, okay? All right. So this is the last file that we'll see, and this is the file where we're going to specify our boundary conditions. Okay, so this is a very important file. So this is a file that you will modify in almost every case that you will get because you need to set the boundary. Okay. Okay. So you, in particular, you will let us specify the velocity field. Okay. So U is kind of the symbol that CFD practitioners use to specify velocity. Okay. Okay. So if you have a boundary condition on velocity, which essentially is going to be your Dirichlet boundary conditions, you do so from the U file. Okay. Okay, so let me go back up to our original problem document here. Okay. So we essentially have four boundary conditions for velocity, right? So we have the top wall, right? So the top wall is moving to the right, and so it's going to have a positive x velocity of 1 meter per second. We have the left wall, which has a velocity of 0 because it's a fixed boundary condition. Okay, so we have u is equal to 0 here. We have the right wall, which also is a fixed wall, so u is equal to 0 on that right wall. And the bottom, we also have a fixed wall, so u is equal to 0 down there. Okay? Okay, so let's go ahead and see how the boundary conditions are specified. So let me clear my drawings here. Okay. Okay, so first couple things that we see here is first thing is that we have this kind of field called dimensions. Okay? Okay, so whenever you're specifying any kind of boundary condition, you need to specify the dimensions of the quantity that you are defining. Okay? Okay, so this is kind of a strange format, but let me go ahead and kind of scroll down in the PDF. You can kind of see what this format is. Okay. Okay. All right, so the way that OpenFOAM defines dimensions is it has this kind of seven entry kind of vector here, where you define kind of the powers of each of those dimensions. Okay, so the order of entries here goes mass. So the first entry is mass, second entry is length, third entry is time, fourth entry is temperature, fifth entry is quantity, and so that's defined as like molar quantity. And so if you're doing some kind of mass transport equation, so like if you want to see simulate contamination, okay. Sixth entry is current, so that is electric current, and the last entry is luminous intensity. And so if you're simulating a firefly or you're simulating a glowing fish or something like that, okay. So for the most part, we're doing just pure fluid simulation. So the last four entries, those are almost always going to be zero. Um, if you want to simulate kind of a heat transfer situation, you can do that in OpenFOAM as well. Okay. All right. So you can see here that for velocity, we have dimensions of length of 1, and then for time, we have -1. So that means our dimensions here is going to be length over time. Okay. All right. And which is exactly the dimensions of velocity. So velocity is length over time. Okay. Okay. Good. All right. Next thing we're setting here is these are the initial conditions. Okay. It's kind of one line here, but it actually does a lot. Okay. And so we'll talk about this after spring break, but whenever you run a time-dependent simulation, you have to initialize your solution field to have some kind of value, just because it has to have some stuff. Okay. So the easiest way or the easiest initialization is just to set the solution to be 0 everywhere. And so that's what we do here. So we say that internally at the beginning, we have a uniform field where every cell is going to have a velocity of 0, 0, 0. Okay. Right. So in most situations that we're going to do in this class, we're going to have a 0 initialization, right? In fact, I think in all cases. So, usually you have to have a very good reason to have a non-zero initial condition. Usually if you're running some kind of fluid structure interaction simulation, you may want a non-zero initialization. But for now, a 0 initialization makes the most sense for everything that we do. Okay. Okay, and then finally we get down to the boundary conditions. And so to start specifying the boundary conditions, we denote the field as boundary field. Okay, and we are basically setting our 3 different regions here. Okay, so the first one is we have moving wall. So remember, we set the name moving wall back in our block mesh dictionary file. So this name kind of corresponds to the name that we set there, right? And so if you want to basically call that wall something different, then you can name it differently there, right? Just make sure that the names that you set in block mesh dictionary match with the names that you set in the U file here, okay? Okay, so for this particular wall here, we are setting this value to have a fixed value. So it's going to be a value that's going to be present at all times. And we're setting a uniform velocity of 1, 0, 0. Okay, so this means for that wall, we're setting a velocity of 1 meter per second in the x direction. Okay. All right, so basically defining the vector of velocity for that wall is 1, 0, 0. Okay. Okay. All right. So the next boundary condition we're going to set is going to be for all of our fixed walls. Remember, so when we define fixed walls in our block mesh dictionary, we define 3 different surfaces because they're all going to have the same boundary condition. Okay. And so that's going to be a no slip type. And so that means our velocity on those fixed walls is going to be 0. Okay. So no slip is a special type of boundary condition where we say the velocity is 0. You can accomplish the same thing. So you can say that for the fixed walls, we're going to have a type fixed value and just say that is 0, 0, 0. That's accomplishes the same thing. But since no slip is so common in CFD, they just create a special command for it. Okay. And then for the front and back surfaces, remember, those are kind of the special surfaces that we have. Even though our simulation is technically a 3-dimensional simulation, we're treating it as if it were a 2D simulation. And so we set a special boundary condition called empty on those surfaces. Okay. Okay. So the U file here, it's a fairly short file, for our case, because our boundary conditions are simple. But this is a very important file for us to. Okay. All right, any questions on the U file? Yes,
If there's multiple velocities, different directions, are they all going to be the same view file?
exactly. Yeah. So basically, all velocity type boundary conditions will be in this file. You would just have different entries for different surfaces. So actually, so that's a good point. So, for one of the problems that I'm going to have you do after this, right? I'm going to have you change the boundary conditions, right? And so one way to do that is, let's say you have your box, right? Right now the top surface is moving that way. Let's say you want to add a boundary condition where the bottom surface is also moving in that direction, okay? Um, and so the way you would do that is you would go back to block mesh dictionary. You define another surface, and so you define kind of another block and say that, define these vertices as another surface and give it a name so that we can refer to it here. And then we can go in this file, we create kind of another section here. So we can call it, maybe bottom wall. So bot wall, okay. And then we give it the same kind of uniform velocity, just like we did with, yeah. Questions?
So what would happen if you were to give some velocity in this particular case in the same direction?
So if you were to give it in the Z direction, so when you set an empty boundary condition, it does kind of something interesting called a I call it a symmetry condition, although there's another name for it. Basically, the way that OpenFOAM is setting this is that any velocity that comes out the Z direction this way, it just gets repeated and just kind of fed back to the back surface. And so if you set a velocity going in the Z direction coming out of the page, that velocity is actually just going to return back into the backspace. Yeah. Yeah, you typically don't want to do that because that would kind of break things a little bit. But that's if there were any kind of out of plane flow, that's what would happen. Mhm. Okay. Question, yes.
Well, in this case, what's the difference between having the fixed walls at no slip and then the front and back at empty?
Yeah. So no slip is a condition where we set the velocity just equal to 0. And so you'll see that, on the lateral surfaces in the bottom, the fluid is actually going to stick to that surface because it's sticky there. But for empty, fluid is allowed to kind of slip past an empty surface, and it's allowed technically to pass through it, but it's going to be almost as if it's not there. So yeah, so empty is kind of a special case because we are running kind of a 2D simulation, but no slip is actually saying, the velocity is equal to 0 on these surfaces. Yeah. Mhm. All right. Any other questions on the boundary conditions here? Great questions, guys. Glad you guys are asking these questions. Okay. Okay, so that's the velocity boundary condition. Right. Next one we're going to look at is P. So we're going to do Vim P. Okay. So P stands for pressure, right? And so the pressure boundary conditions in this case are not that interesting. So pressures would essentially be kind of like a Neumann boundary condition. We're not setting any in this case because all of our boundary conditions are Dirichlet. We're setting velocity conditions everywhere. But if you did want to set a pressure condition, this is where you would. Okay. Okay. So the only things to really note here are the dimensions. And so you can see that we have dimensions of length squared over time squared. Okay. Which is kind of a strange unit for pressure, right? So pressure, I think normally we associate as force divided by area. So what is time doing, right? So remember I mentioned earlier that OpenFOAM uses a kinematic version of Navier-Stokes where we divide everything by the density, okay? So when you divide pressure by density, you get something called a kinematic pressure, okay? Okay. Where kinematic pressure kind of has this kind of weird units of length squared over time squared. So it is a real pressure, right? But if you want to kind of convert this to kind of a traditional pressure, you would just multiply it by the density, okay? But that's kind of what those kind of weird units are, okay? Just like the velocity, we're going to initialize with a 0 pressure everywhere, okay? So, but pressure is a scalar, so there's no vector there, so it's uniform 0. Okay? And you can see for every surface here, the moving wall and the fixed wall, we're setting 0 gradient. So we're essentially saying that the pressure, there's going to be no boundary condition on pressure. Okay, so the pressure is going to be 0 gradient. Okay. And then for our front and back surfaces, we use our special boundary condition empty because again, we're simulating this as kind of a 0D or excuse me, a 2D situation. Okay. Any questions on the P file? Okay, I'm realizing that we're not going to finish today, and so we'll pick this up again on Wednesday. But I did want to at least get the simulation running, just so that you guys can actually do that. And I realize there's probably going to be some issues with that. Okay. But before we get out of here, you can see that there's several other files here. So there's epsilon, there's k, there's nu tilde. This is not nut, it's nu t. Okay. Um, and there's omega. Okay. So these files, we're not going to concern ourselves with. So sometimes they may be in a case like this, and so if you're copying kind of a tutorial from OpenFOAM, you might see them. Those are variables that have to do with the turbulence. Okay, but since we're not really caring about the turbulence too much, we're just going to ignore them. But they have to be there because technically we are simulating turbulence. Okay. Okay. All right. So that's all. All we did is we just kind of looked at the case. Okay. But to actually run the simulation, we're actually going to do that now. Okay. So there's two steps you actually have to do to run the simulation. So the first thing you have to do is you have to create your mesh. Okay. Okay. So to create the mesh, make sure that you are in your cavity folder, right? So you're not inside 0, you're not inside constant, you're not inside system. So when you type ls, you should see 0 constant system. Okay. So to create your mesh, you're going to run a special command called block mesh. Okay. So that's block mesh, always one word, but the M in mesh is capitalized. Okay. So go ahead and hit enter. Okay. And then what that's going to do is that it's going to create your mesh. So you're going to see a bunch of text is going to get dumped to your screen. Okay. But if everything goes well, you should see the following outputs. And so, the main thing to look for is this information here on the mesh. So you should see a box that says mesh information. Okay. It's going to tell you the size of your box here. It's going to tell you the number of grid points. And so this mesh has 882 points. It's going to tell you the number of cells. And so this is actually the most important setting here, right? So this tells us that we have 400 cells in our mesh, right? And that makes sense because remember our mesh was 20 by 20. Okay. So that's 400. It's going to tell you the number of faces and the number of internal faces here. Okay. Right, and it's going to tell you the names of all the different patches here. So moving wall, fixed wall, and front and back. Okay. All right, so was everyone able to create their mesh? They were able to see this screen here? Okay, good. All right. So this is one of the unfortunate things with OpenFOAM is that there's no easy way to view the mesh. So if you learned, if you took like say finite elements last year or last semester, you'll see that after you create the mesh, you can view it right away. There is a way to view it, but it's usually, if you create your mesh and everything looks good here, usually there's no reason to view it because you can trust that it's okay. Okay. Okay, and now that we've finally set all of our settings, we're finally ready to run the simulation. Okay. So to run the simulation, it's just a very simple command. It's actually going to be clear, just so we can kind of see everything here. Okay. So the command to run the simulation, and you're going to do it from the same folder that you ran block mesh from. The command is called foam run. So foam and then run, always one word, but run is capitalized. Okay. I'm waiting to hit enter. So some of you may have hit enter already, because what's going to happen is that it's going to just throw a bunch of text to the screen. It's going to feel kind of overwhelming, but we'll kind of go through it really quickly right before we end. Okay. Okay. So I'm gonna hit enter. Since this is such a simple case, it should run in just like 7 seconds or something. Okay. Right, you're gonna feel like you're in the Matrix. Da da da. Okay. All right, and we're done. And so this simulation on my computer ran for about 3.35 seconds, which is pretty good. I mean, computer's feeling pretty good today. Okay. Okay, so now we have our results. Okay. Okay. So to view the results, we'll actually do that next time because there's actually quite a lot to talk about with the post-processing. But one thing to check whenever you run your simulation is that you should see at the end of every time step, you'll see that there's going to be some message here called the Courant number. Okay. So it's going to tell you the mean Courant number. So that's the average Courant number for your entire simulation, as well as the maximum Courant number. Okay. We'll talk more about what the Courant number means after spring break, but you can think of this Courant number as like a measure of your stability. Okay, remember we've talked about the Peclet number. So Peclet number is basically a measure of stability for steady simulations. But when you have unsteady simulations with a time step, the measure is Courant number. Okay. And basically you want your Courant number to be less than 1 for a stable simulation. Okay. And so in this case, we do have that. So our mean Courant number is, that. Our max is 0.25. So we have a stable simulation, which is good because this is a prepackaged tutorial. So I hope OpenFOAM would give us something that's not unstable. Okay. Okay. All right. So unfortunately, that's all the time we have for today. We'll pick this up on Wednesday. We'll talk about post-processing. So if you're having trouble with the simulation, I'll kind of make some round today. I have your midterm, so don't forget to leave without your midterm exams. But we will talk about this again on Wednesday. So thank you guys for coming today. Hope you guys enjoyed the first. I know it wasn't much, but I think hopefully Wednesday will be more fun when we actually see the results. But yeah, hope you guys have a good rest of your day. Someone say my name? What's up? Yeah. Okay.
Hello. Don't rush me.
The version A and version B should be separated.
Is mine on top?
No, I didn't want to make it obvious that you took it today, so I said I flipped it.
Did I get the polarity right? Okay.
Yeah.
Oh, I did?
Yeah, you did.
I'll look and see.
All right, let's split into two bias.
I should have put it like highest score, lowest score.
No.